Day 2 of 4-6. So, if you flip to the second page, we did cotangent yesterday, right? We did just plain cotangent, well, not really plain, we did plain tangent, right? But I told you that this one looks like cotangent because of the reflection, right? So let's actually look at what cotangent is. So this is not plain cotangent.
I have a question.
Yeah.
If you have cotangent and then you have like a negative inside,
Then it look like tangent. Mhm. Are the periods the same for tangent and cotangent? Yeah, so look at the original over here, right? So the very first page is your original tangent and cotangent, right? Do they have the same period? The periods both, this one's pi and that one's pi, right? Do they have the same asymptotes? No, that's the different, there's two differences between tangent and cotangent. One difference is where the asymptotes are placed.
it will still look different.
Yes, and the other difference is the order of the curve, right? Tangent goes from the upper right down, and cotangent's upper left down. So we do have to pay attention to those. All right, so, second page. What do I have to find first? Just look at the equation and tell me what you see. See, what'd you say? Bless you. What about the 2? What does the 2 represent? Yeah, it's amplitude, right? So your amplitude is 2. Is that a concern to you in tangent or cotangent? No, not really. Because once you find your asymptotes, that's going to get you the shape of your curve. Remember from yesterday that whatever is happening to x affects your asymptotes because it affects your period. Really, isn't this 2 times the cotangent of 1/3 x?
Why is it?
Because x is being divided by 3, so take x out of the fraction. Don't you have 1/3 x? Okay. So then we're going to find our asymptotes. Do you remember how we did it yesterday? So go back to the very first page. So yesterday we took one period. So I'm going to take this period right here from 0 to pi. Because the asymptotes are different on cotangent than they are on tangent, right? The normal start for this period would be at 0, and the normal end would be at pi, right? So we're going to find our new asymptotes. So we're going to take this x over 3, and we're going to set it equal to 0 because I chose that period. You could have chosen a different period, and you'll still end up getting the same graph as I do. And then we're going to solve that for x. What else am I going to set x over 3 equal to? This is the start of the period. What's the end of the period? What is it? Pi, right? So start of the period, end of the period. Solve these for x. If I were you, I would change these into a proportion and cross multiply and solve. So what does x equal here? What's 3 times 0? So 0, right? So this is one asymptote. And then this time I get x equals 3 pi. So instead of having a normal period width of pi, what's my period width now? 3 pi, isn't it? From 0 to 3 pi. So we've really stretched out the period. So is the curve of cotangent going to be flat or straightened? Remember, a fraction flattens it. Something greater than 1 straightens it. So it's going to look like that, right? Really flat along the x-axis. So let's go ahead and put our asymptotes in, because that's pretty much all I need to know. X cannot equal 0 and x cannot equal pi over 3. So here is 0 at x. And then we need to partition this into 4. So this is pi. 2 pi. 3 pi. 4 pi. Negative pi. So my other asymptote is at 3 pi. Do I have enough room to do Any more intervals? No. Where's the center of this? Between 0 and 3 pi, where's the center? Yeah, 3 divided by 2 is 1.5, right? So I want to go 1 and then 1/2 of a pi. So here's the center. And then my cotangent goes from the upper left. I go through there, down to the right.
Are you not going to like what kind of arc?
No, if you've got the general curve, I'm not super picky because I have artistic issues myself. All right, so then we do have to finish off what we see here though, since the middle is 1, 2, 3, 4, 5, 6 of my hash marks over because I went by fourths. Then I have to go 1, 2, 3, 4, 5. This would be the middle again. So I do have to show the partial that's missing and just off as far as it can go. And then same thing on this side. Yes.
So how did you get that? That's midpoint?
Because from here to here is 3 pi, right? So 1/2 of 3 is 1.5. So I counted 1 pi and then halfway in between. Or you can count the number of spaces you have here. Don't I have 12 altogether? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Split that in half, I get 6. So just count 6 over. So I'm going to count 6 backwards. 1, 2, 3, 4, 5, 6. There's my midpoint, right? And then it should curve this way. And then curve up.
But we only want that, we don't want that.
Yeah, you need to fill out the whole thing. And if you're making the graph yourself, then you can just make it long enough for one period. Well, for tangent and cotangent, I'd like you to try to get 2 periods in. Obviously, this one's so wide of a period that I would probably accept this because it's a very wide period.
But is it like the really narrow ones that we did yesterday?
Then those ones you could make like 4 periods and be totally fine with it. So that wasn't stressful, was it? Okay. The last 2. I'm gonna work you into this. So, are we ready? No? I mean, have you written everything down that you need to for this one? I know you're not ready, but are you ready? You're so funny. All right, so I've written a lot of points here for a reason, or, points here, these bullet points. Remember that cosecant is the inverse of sine, so it's 1 over sine. Cosecant represents this fraction, right? Let's look at the unit circle. So this is 1, 0. This is 0, 1. Negative 1, 0. And 0, negative 1. Sine is x or y? Y. So sine is down here in the denominator. What value for sine, because it's either 1, 0, or negative 1, can that denominator not be? Because remember, we're finding the asymptotes, and the asymptotes are where this is undefined. Where is 1 over sine undefined? So is when sine is 0, right? So sine is it x or y? Y. So where is y 0? Here and here. Agreed? Isn't that at 0? And also 2 pi, but we're going to ignore that for right now. And then at pi. So that means I have asymptotes again at 0 and pi. However, you're going to think that that means that I only have a period of pi, right? Because the distance from here to here is pi. But I'm going to explain to you why it's 2 pi. So let's go down here, and we're going to go ahead and put in, mark this off to go by fourths again. So this is pi. And we're going to have this as Let's go ahead and make this hash mark right here 1, because I want you to have room to actually see the graph, and that'll be 2. So in your vertical scale, I want you to go by halves, only because I'll make sure you can really see the graph. So when y equals 0, cosecant of theta is undefined. Make sure you have that in your notes. When y equals 0, the cosecant of theta will be undefined because it's 1 over sine, and sine is y. Does that make sense? All right, so I'm going to put in my asymptotes first. So the first one we found was at 0. The second one we found was at pi. And if I keep going around the circle, every pi I should have another asymptote, right? So we're going to have all these asymptotes at each pi. And then do it in the negative direction. So I'm going to draw something up here on the board. And I'm going to draw one curve of sine. Because if cosecant is the inverse of sine, don't you draw this on your paper. I just want you to watch what I'm doing so you can understand why. Normally, doesn't sine start here at 0, 0? And then at pi over 2, what happens? It goes up to 1. At pi, what happens? It goes down to 0. At 3 pi over 2, it goes down to negative 1, and then back up to here. So wouldn't you agree that this is the normal sine curve? Okay, but it gets interrupted when it's cosecant here. It no longer exists in here and here, correct? Doesn't this look like a parabola? But cosecant is the inverse of sine. Inverse, if I flip this, wouldn't this go up like this? Wouldn't this curve, when this was supposed to go all the way down to here, wouldn't this curve be reflected in that direction for an inverse? So this part of the sine curve disappears, and this is how cosecant comes about. That part of the sine curve disappears, and you have a parabola going up at pi over 2 at 1. That's where the vertex is. What happens with this one? It goes down, right? It reflects down, but it goes in this direction. It's following the asymptotes, and then this disappears. There is one period, and that's why cosecant is 2 periods long. This is this half of the sine curve that got reflected up, and this is that half of the sine curve that got reflected down. So this becomes 1 full period for cosecant. Yes? All I did was flip the sine curve. Would you agree that this is a normal sine curve?
Yeah. Oh, you just, okay.
All I did was break it here at the asymptote, and I flipped this up, and I flipped that down because cosecant, sine is the inverse of cosecant, right? Or vice versa, however you want to look at it. Does that make sense what I just did?
Yeah, you just.
So that's why the green is the proper graph. That's your graph, 1 period of cosecant. Yes.
Really in my part.
Yeah.
That's it?
But I made it easy, didn't I?
Yeah.
Now you, Kelsey, how you doing? Are you good? But do you understand why I came up with this? I didn't want to throw this at you without explaining to you where it came from.
Well, how does that relate to what you're graphing?
That's what we're graphing.
That's what we're graphing?
That's what we're graphing. Okay? That's what we're graphing. You have to know that the height of sine is 1, right? So with cosecant, it's going to start, its first normal period is from 0 to pi. Well, half of its period. In the middle of that is pi over 2. So at pi over 2, the height, so to speak, even though cosecant doesn't technically have an amplitude, because it goes infinitely here and infinitely there, But the vertex is at 1. Isn't that our normal height of our sine curve? So your vertex goes here at 1. You have to know that cosecant opens up here. Just turn it off. You have to know that it goes up and then it goes down. What do you think is going to happen over here? Then it's going to go up. Stop talking. Then it's going to go up, right? And then over here it's going to go down, right? Over here what's going to happen? Yeah, so it's down. Well, I was supposed to hug the asymptotes though. But my point is, if you get this started correctly, then won't the rest fall into place? You have to have the vertices in the right spot. Now, will the vertices move? Yes, they can move. But we're not going to do that yet. You just have to know, where do your normal vertices go? They go where the normal sine curve vertices would go. There, there. We don't put the ones on the x-axis because that's where the asymptotes would hit. There, there. Matt?
So,
There.
so then what are our key points?
Your key points are the same key points as the sine curve. Well, you notice I'm not going to ask for them though. But you can mentally think of them, that they're the same, except when I hit the x-axis. So normally we'd have 0, but there's an asymptote there, so we put an asymptote instead of a key point.
Ah,
Right? Then this would be the next key point for sine.
okay.
But because it's cosecant, we're going to go up here. This is the next key point, but it's an asymptote. Every other key point is an asymptote. Does that help?
Yes.
Okay. So let's finish this on our paper. So I can take that away. Oh, who did? Sorry, I can't see. I've got the glare. Yes,
She has
Matt.
a question.
No, I'm good.
Are you good? You
Yeah.
sure?
I was gonna ask what we're drawing on the paper. and then we just-
This is what we're drawing on the paper. Okay, so here we go. So because at sine I would normally be here, but it's an asymptote, our next key point at sine would be here. But because it's cosecant, I'm flipping it up. So you get this series of parabolas opening up or down. The next key point is here, but it's an asymptote. Next key point is here, but it opens down because it always switches direction. And then just follow that pattern all the way through.
So this is all that cosecant do.
That's it. But as all of these, you have to know where does it start and kind of what direction does it go in. And so the vertical asymptote would be at every pi, and you can put a slash there because it does not equal that. All right, so you ready for the next one?
Yay.
The next one is just plain secant, and then we're going to do something with them. Of course. Hey, you've gotten along so far. This is the last one that we have to adjust.
Really?
All right, so now we have to look at secant. So that just gives us 2, 4, 6 total. And each one of those groups of 6, you can group them into groups of 3, right? The sine and cosine are very similar. Tangent and cotangent are very similar, and you're going to see that secant and cosecant are very similar. All right, so let's look at the unit circle again. I told you it was very important, right? 1, 0, 0, 1, negative 1, 0, and 0, negative 1. What is secant equal to? 1 over cosine. Cosine is what? X. So we're really looking at 1 over x on the unit circle. Bless you. When is x undefined? At 90, which would be here, right? And at 3 pi over 2. What does that tell you about your asymptotes? Where's your first asymptote? At 90, which is pi over 2. And then your next asymptote will be at 3 pi over 2. Are you going to have a period of 2 pi or 1 pi? 2 pi because it's similar to cosecant, right? And the graphs are going to look similar too. All right, so I'm going to start with, and you might want to add this up here also, that when x equals 0, secant of theta is undefined. So I'm going to put my, I have to mark this off first. So mark this off in the force. And again, we're going to mark this as +1 and this is +2. So on the vertical, we're going to go by halves, so we don't squish it so much. -1 and -2. So let's put in our asymptotes. So our first one starts at pi/2, which is halfway between 0 and pi. And the next one's at 3pi/2. 3pi/2 is halfway between pi and 2 pi. What's the distance between the asymptotes? Pi. So between every pi, directly in between, you're going to have an asymptote. Now I'm going to do it again, and you can always do this if you forget how the sine or cosine or how the secant and cosecant curve works. So cosine, we normally would start at 1, wouldn't we? And then we would go down here to 0, right? And then down here we would go to -1, back up to 0, and back up to 1. But I want to look at it in 2 pi. Since my asymptotes are here, I need to fill this curve out over here. Doesn't it go back down to 0 here? Right? This is your normal cosine, is it not? True? And so this would continue on because I want a full 2 pi for my period. So would it bother you if I erase this part now? Now it kind of looks like the sine curve, doesn't it? Right? But at the y-axis, isn't it at 1? So we know it definitely isn't the sine. All right, so this is an asymptote, so make that go away. And then remember, secant is the inverse of cosecant. So what's going to happen? Yeah, so this is going to flip up. Just like the last one did, but it flips up in a different place, doesn't it? And so this one goes away. And then this one does what? Flips down. And then that goes away. So it looks very similar to the cosecant one, right? It's like it's horizontally translated, right? So I'm going to erase that and actually write it on paper. So again, know where your key points are. On the y-axis, a key point is at 1, that's a starting point. And I know that it's going to go up. My next key point would be down here, and I know that it goes down. And you can just follow that pattern. Isn't it frightening how easy you accepted this today? Either that or you're like a whipped puppy dog. Just
No.
Sine and cosine were harder.
only because you hadn't seen them before, right?
Wasn't
No,
it?
I still don't like this
Yeah.
one.
I still don't get it. Like,
Sine and cosine, really?
Yeah, it's impossible.
Well, we'll go back and look at it again.
It's most of the, yeah, it's the key
It's
points
the
that
good
are-
ones.
We can talk about that again today when we go over your homework. because you're right, it is the key points. If you have your key points, then everything's good. Key points deal with your period also. If your period changes, your key points change. All right, so let's look at this last one down here. Now we're going to graph the secant of 2x. Ooh, isn't the secant what we just did above? Okay. So what are your normal, pick a normal period up here. What was a normal period? Well, a normal distance between two asymptotes here. The first one we had was pi over 2 and 3 pi over 2, right? So we can use this one. You can use whichever ones you want, but I'm going to use this one that goes along with the unit circle. So I'm going to use pi over 2 and 3 pi over 2. Isn't that where your original asymptotes are? Doesn't this change our period, the 2 in front of the x? True or false? It's never changed anytime we've done any of these, sine, cosine, tangent, whatever. So you're going to take that 2x, mind you, our amplitude has not changed, but our asymptotes, you're going to take that 2x and you're going to set it equal to your first asymptote. I choose my first asymptote to be this pi over 2. Then you're going to take the 2x, or sorry, the 2x, that was right. And you're going to set it equal to what? What's your ending? If this is your first. Your ending asymptote would be 3 pi over 2. Now you have to solve for x. So put this over 1 and this over 1 and start to solve. 2x times 2 is 4x equals pi. How do you solve for x? So your first asymptote is now pi over 4. Then for the next one, 2x times 2 is 2x equals 3 pi. 4x we have. And then divide by 4, x is equal to 3 pi over 4. So it's good that we're counting by fourths on a graph, right? Because all we have to do is get the first set in, and then the next set will be fine. What's the distance between these two? What's 3 pi over 4 minus pi over 4? 2 pi over 4, which is pi over 2. What was the difference between these two? A whole pi, right? So have we shortened our asymptotes or lengthened our asymptotes out? Shortened. So we should have more. This is going to squeeze in right here, and we're going to end up with more of these graphs. So start by labeling your graph. And again, your vertical axis go by paths. And then put your first asymptote in, which is pi over 4. Your next asymptote is 3 pi over 4, which is still shy of a pi. So there's a ton of them in here, aren't they? So every 2 pi I have to put in an asymptote. So continue that pattern. What's wrong? I hear whispering.
There's so many ambiguities.
Yes, there are.
Do we have to make them all?
Yes. The graph is given to you, yes.
Well, let's say.
If I were making my own graph, would I make this many? Absolutely not.
Okay. See, that makes more sense, because I was going to say if I ever do my homework, maybe I have to make this one. But that's not good.
I did that.
Imaginary numbers.
So if this was the, I put a highlight right here because this was the first set of asymptotes that we chose. Didn't I choose it off of this set of asymptotes here? Isn't the normal point here below the x-axis and opens down? So same thing occurs here. This point is here at -1 because the amplitude has not changed, and it opens down. And if you think about it, you could have chosen this one too. This would be at +1 on the actual y-axis itself, and it opens up. So however you want to start your pattern, there it started.
So small.
It is tiny. In the bottom of this, down here, just kind of talks about, puts all 6 of them together, and they're all your normal sine, cosine, tangent, cosecant, secant, and cotangent. So no amplitudes, no period changes, no horizontal or vertical shifts. And these are what your curves are. You've got to know those curves. That's your normal curve for that. So study those. Study the differences and how to find them. All right, any other questions before we start going over homework? Okay.